Welcome back. Today we're going to look at Quicksort. That was named as one of the most important algorithms of the 20th century and is widely used for system sorts and many other applications. Last lecture we looked at merge sort, another classic sorting algorithm that's used in many systems, and today we're going to look at Quicksort, which is used in many others. You can even get a Quicksort t-shirt nowadays. So what is the Quicksort method? It's also a recursive method, but the basic idea behind Quicksort is that it does the recursion after it does the work, whereas merge sort did it before it did the work. So the idea is first randomly shuffle the array. That's an important step that we'll talk about later. And then partition the array. So that's to divide it so that for some value j, the entry a of j is in place in the array. There's no larger entry to the left of j and no smaller entry to the right of j. Once we have the array partitioned in that way, shown here in the middle, right here we have k in its position and we have everybody to the left, there's nobody greater than k, and everybody to the right, there's nobody less. Once we have it arranged in that way, then we recursively sort the two parts, sort the left part, sort the right part, and then after those two things are done, the whole thing is sorted. This method was invented in 1961 by Tony Hoare, who won the Turing Award in 1980 for this and other work. So let's look at a demo of how Quicksort partitioning works. The idea is to arbitrarily choose the first element to be the partitioning element. Since we shuffled the array, that's a random element from the array. And then we're going to maintain an I pointer that moves from left to right and a J pointer that moves from right to left. Let's look how it works in the demo. So we start again by picking k as the partitioning element, and then our method is to move the I pointer from left to right as long as what we have is less than the partitioning element, and move the J pointer from right to left as long as it points to an item that's greater than the partitioning element. So in this example, the I pointer stops right away because it's pointing to an R, which is bigger than the partitioning element. The J pointer decrements until it gets to the C, which stops there because that's less than the partitioning element. And so now what's going to happen is those two elements are out of place. The partitioning element's in between them and they're in the wrong order. So all we want to do is exchange those and then move on. Now we increment I as long as it's pointing to an element that's less than the partitioning element. Stop here at T because that's bigger. And now we decrement J as long as it's pointing to something that's bigger than the partitioning element. Stop here at I because that's less. Again, T and I are in the wrong places. If we exchange them, we'll maintain the invariant that everything to the left of I is less than the partitioning element, or nothing to the left of I is greater than the partitioning element, and nothing to the right of J is less than the partitioning element. So exchange them, increment I as long as it's less, stop at L. Decrement J as long as it's greater, stop at E. Those two elements are out of position, so exchange them. Now increment I, stop at the L, which is greater than K. Decrement J, stop at the E, which is less than K. And now at this point, the partitioning process is complete because the pointers have crossed and we've looked at everything in the array. In fact, J points to the rightmost element in the left subfile. It's everything that's not greater than K, so we can just exchange J with our partitioning element, and now we've achieved the goal of partitioning the array so that A of J is in its position, nobody to the left is greater, nobody to the right is less. Now the code for partitioning is straightforward to implement. Down below shows the state of the array before partitioning, during, and after partitioning. So in the end, the J pointer is pointing to the partitioning element V, which was in position V in the first place. All during the partitioning process, the code is maintaining this invariant, where everything to the left of I is less than or equal to V, everything to the right of J is greater than or equal to V, and we haven't looked at things in between. So Finding incrementing I as long as it's less is a simple while loop, and then we put a test to make sure we don't run off the right end of the array. And decrementing j as long as it's pointing to a bigger element is similarly just a while loop where we put in a test to make sure we don't run off the left end of the array. Then there's a test to see if the pointers cross, swap the elements at I and j. When we get to the pointers cross, we break out of the loop and exchange the partitioning element into position. So that's a quick implementation of the Quicksort partitioning method. Now, Quicksort itself then is going to be a recursive program that uses that partitioning method. The first thing we do is the public sort method that takes the array of comparable items as its argument is going to do a shuffle, and that shuffle is needed to make sure that we can guarantee that the performance is going to be good. And then it calls the recursive method that takes as arguments the limits of the subarray that's going to be sorted. So then partitioning simply does the partitioning, tells us which element is in position, and then recursively sorts the left part, that's low to j minus 1, and then the right part, that's j plus 1 to high. That's a complete implementation of Quicksort. Again, as with merge sort, studying the recursive trace is instructive, and this one is kind of upside down as compared to merge sort. The first line shows the partitioning where k is put into position. Then the method calls the sort for the left subfile first, and then that's going to be partitioned on this E, and so forth. And eventually we get down to small subfiles. Actually, our code doesn't do anything at all for subarrays of size 1, so we just leave those in gray. And then it does the right subfile and so forth. Again, studying this, a trace like this gives a good feeling for exactly what's going on in the recursive program. Let's look at an animation of Quicksort in operation. There's the partition. Now it's working on the left. Now it's partitioning the right. Now it's working on the left part of the right. Now it's partitioning what's left, doing the left part of that. And working from left to right by dividing each subarray in half as it goes. So let's consider some of the details in the implementation of partitioning with Quicksort. So first thing is it partitions in place. You could use an extra array and the partitioning code would be a little bit easier, but one of the big advantages of Quicksort over merge sort is that it doesn't take any extra space. It gets the sort done in place. Now, you have to be a little bit careful with terminating the loop. When we give you working code, it's not hard to see why it works, and you might go through the exercise of trying to implement Quicksort without looking at our code. And you'll find that testing when the pointers cross can be a little bit tricky, particularly in the presence of duplicate keys. Also staying in bounds. Actually, in our implementation, the test of the J pointer running off the left end is redundant. Why is it redundant? Well, the partitioning element's sitting there, and it'll stop when it hits the partitioning element. But the other test is not in our implementation. And the key thing, one key thing is that the way that these implementations work, if the file is, the array is randomly ordered, then the two subarrays after partitioning will also be randomly ordered. Actually, some implementations of Quicksort out in the wild don't have this property, and they suffer a little bit in performance. That random shuffle at the beginning is important and needed for guaranteeing performance. And the other thing I've referred to but not talked about in detail is the presence of equal keys. You might think it would be better to handle equal keys in some special way, and we'll talk about that in a second. But this general purpose implementation stops the pointers on keys equal to the partitioning item's key, and we'll take a look at why that's important in a minute. So now let's look at the running time estimates about why we care about Quicksort versus merge sort. This is extending the table we looked at last time. And you can see over in the right column here, Quicksort is quite a bit faster than merge sort. And again, a good algorithm is much better than having a supercomputer. Even on your PC, you can sort a huge array of 1 million items in less than a second and 1 billion items in only a few minutes. So again, this sort of timing is why Quicksort is so widely used, because it's simply just faster than merge sort. Well, in the best case, Quicksort will divide everything exactly in half, and that makes it kind of like merge sort. It's about n log n. And in the worst case, if the random shuffle winds up putting the items exactly in order, then partitioning doesn't really do anything except find the smallest, peel off the smallest item, kind of discover that everything to the right is greater. That's a bad case, but if we shuffled randomly, it's extremely unlikely to happen. The most interesting thing about the study of Quicksort is the average case analysis. This is a somewhat detailed mathematical derivation, but it's worthwhile going through the steps to really get a feeling for why it is that Quicksort is quick. So what we do is, as we did for merge sort, is write down a mathematical recurrence relation that corresponds to what the program does. In the case of Quicksort, the number of comparisons taken to sort n items is n plus 1 for the partitioning, plus what happens next depends on what the partitioning element was. If the partitioning element is k, any particular value happens with probability 1 over n. And if it's k, then the left subfile has k minus 1 items in it, and the right subfile has n minus k items in it. So for every value of k, if you add those up, the probability that the partitioning element is k plus the cost for the two subfiles, we get this equation. This looks like a fairly daunting equation, but actually it's not too difficult to solve. First thing we do is just multiply by n and collect terms. So NCN, n times n plus 1, and then these terms, every size appears twice, so it's twice the sum of from C0 to Cn minus 1. That's a simpler equation already. Now what we can do is get rid of that sum by subtracting the same equation for n minus 1. So NCN minus n minus 1 Cn minus 1, and then the, n times n plus 1 minus n minus 1 times n is just 2n, and then the sum collapses, just leaving the last term. This sum minus the same sum for n minus 1 just leaves the 2Cn minus 1. Now that's looking like a much simpler equation. Rearrange the terms. So we get n plus 1 Cn minus 1, and then divide by n times n plus 1. That's a kind of a magic step, but we'll see that makes it possible to solve the equation easily. Because that equation with Cn over n plus 1 equals Cn minus 1 over n is an equation that telescopes. The first term at the right is the same as the term on the left, so we can apply the same equation. So it was 2 over n plus 1. We apply for n minus 1. We get 1 less here, and we throw out a 2 over n. And continue that way, throwing out 2 over decreasing numbers all the way down till we get down to 2 elements, or C1, which is 0. Substitute the previous equation, telescope, and then that gives us an easy sum that we can approximate by an integral. It's 1 over x from 3 to n plus 1, and that's a pretty close approximation in this case. And that approximation gives us, it's about 2 n plus 1 natural log n comparisons for Quicksort, about 1.39 n log n. That's the average number of comparisons taken by Quicksort. And actually, for a random permutation of the input elements, which is what we do with the shuffle, the expected number of comparisons is concentrated around this value. It's very likely to be very near this value as n is large. So the worst case, Quicksort is quadratic. So complexity is going to tell us that it's a quadratic algorithm. That's what its worst case is. But with the random shuffle, it's more likely that this lecture will end because of a lightning strike, or your computer will be struck by a lightning bolt. So we can discount that. The average case, which is extremely likely for any practical application, is going to be about 1.39 n log n. So that's more compares than merge sort uses, but quicksort is much faster because it doesn't do much corresponding to each compare. It just does the compare and increment a pointer, whereas merge sort has to move the items into and out of the auxiliary array, which is more expensive. So the random shuffle is a key for good performance in quicksort. It gives us the guarantee that the worst case is not going to happen, and also it allows us to develop a math model that we can go ahead and validate with experimentation. You run quicksort and you count compares. If you did the random shuffle, it'll be about 1.39 n log n compares, and its running time will be proportional to n log n, and it'll be a fast sort, and that's what people do, and that's why people use it. Now there are some things that you have to watch out for with quicksort because the implementation is a bit fragile and it's easy to make mistakes, and you'll find textbook implementations or implementations out on the web that wind up running in quadratic time in certain situations. You have to be a little bit careful of that, and even if everything is randomized, if there's lots of duplicates and the implementation's not done quite right, the quicksort might take quadratic time. So let's summarize the properties of quicksort. It's in place. It doesn't use any extra space. The depth of recursion, so that's again dependent on the random shuffling, is going to be logarithmic. You can limit the depth of recursion by always doing the smaller subarray before the larger subarray, but that's not really necessary nowadays as long as you've done the random shuffle. Oh, and by the way, quicksort is not stable because partitioning does one of those long-range exchanges that might put a key with equal value over a key, another key with the same value. So it's a little more work to make quicksort stable, maybe using extra space. So what about in practice, this is our fastest sorting algorithm, and there's a few ways to make it even faster. And we looked at some similar things with merge sort, and it's definitely worthwhile implementing for quicksort. First thing is small subarrays. Even quicksort has more overhead than you want for a tiny array like one of size 2 or 3 or 4. So you can implement it to cut off to insertion sort for small arrays. And the exact number they use is not too critical. Anywhere between 10 and 20 will improve the running time by maybe 20%. Also, you could just not do anything for small arrays and then do the insertion sort in one pass at the end. So that's a first improvement. Second improvement is to try to estimate the partitioning element to be near the middle rather than just arbitrarily using the first element, which on average will be at the middle. So one thing that we can do is sample the items and then take a median of the sample. That's actually not worth the cost for large samples usually, but for 3 it's worthwhile. Slightly reduces the number of compares, increases the number of exchanges paradoxically because more exchanges are required when the partitioning is right in the middle. So that'll also improve the running time by maybe 10%. So this is a summary of the optimized quicksort with cutoff to small subfiles and median of 3 partitioning. So partition usually happens pretty close to the middle when you do that sample and median of 3. And then small subfiles can just be left unsorted to be picked up with insertion sort right at the end. So this gives a feeling for the number of items that have to be touched during quicksort and kind of an explanation for how it gets the sort done so quickly. That's a summary of quicksort, our best sorting algorithm that we've seen to date.